going to start by simplifying exponential expressions, which is actually like an Algebra 1 skill the first time you learned it. We'll just do some more challenging examples towards the end. But first, when you get a power to a power, x squared to the third, power to a power, you multiply those exponents. So that's 2 times 3. So it's x to the 6th. Power to a power, you multiply exponents. So for this next example, we could do the same thing, power to a power. Square root of 2 times the square root of 2. It's just regular 2. And since that's a number to an exponent, let's go ahead and do that. 4 squared is 16. These next couple examples are a little bit different. They're not a power to a power. Instead, they are being multiplied together. X to the 4th times x to the 5th. So now we're going to add exponents. When you're multiplying, you add exponents. So this is 4 plus 5. So that's x to the 9th. This next one, still the same idea. We're multiplying. They have the same base. So we're going to add the exponents. So we're adding 1 plus the square root of 5 plus 1 minus the square root of 5. Add the exponents together. Now, the most common mistake that people will make with this is by multiplying your bases. You never do anything with the base. The 3 and the 3, you just keep it a 3. You don't multiply bases, you just add the exponents. So when we add the exponents, we have 1 plus 1 is 2. Positive square root of 5 and a negative square root of 5 cancels out. So 3 squared, since that's a number to an exponent, let's do it. We get 9. So these last 2 examples, we did multiply things with the same base. Now we're dividing things with the same base. When you multiply, you add exponents. So when you divide, you subtract exponents. So we got x to the 10 minus 6, which is 4, x to the 4th. Same thing, even if they're a little bit weird as exponents, the bases are the same, so we subtract. So we do 6 plus pi minus 4 plus pi. You do need to remember to make sure that you distribute that exponent, or the negative sign. So it's really 6 plus pi minus 4 minus pi. So now when we keep the base, which is 5, 6 minus 4 is 2. Pi minus pi cancels out. So it's really just 5 squared, which is 25. Whenever there's numbers, just do the actual multiplying it out. Here's another power to a power, which means we're going to multiply our exponents together. But keep in mind that the square root is really an exponent. So the square root of 10 is really 10 to the half. So this is 10 to the half to the square root of 3 to the second. Whole lot of exponents. But whenever you have a power to a power, even to another power, you just multiply all your exponents together. So we're multiplying 1/2 times 2 times square root of 3. 1/2 times 2 is just 1 times the square root of 3. So we just get 10 to the square root of 3 because the 1/2 times 2 cancels out. We've got one more just like that. Again, square roots are like half powers. So this is 6 to the 1/2 to the pi to the 4. Since it's power to a power, you just multiply. 4 times 1/2 is 2 times pi. So it's 6 to the 2 pi. You could actually also think of it as 6 squared to the pi, which would be the same thing as 36 with pi as the exponent. Since it was a number to the squared, we could actually do that. 6 squared is 36. So if a to the m equals a to the n, then m equals n. Just means if you have things with the same base on both sides, bases don't really matter. The exponents have to be the same. So let's take this first example, 4 to the x. And we want it to be 4 to the x equals 4 to some power. So that way the bases are the same, so we can figure out what x equals. So 64 is 4 to the third power. So since we have 4 to the x equals 4 to the third, that means that x has to equal 3. And that's it. Similar idea for this next one. Just remember that 5 squared is the same thing as 5 to the 1/2 power. We have the same base on both sides, which means the exponents have to be equal. So 4x plus 1 must equal 1/2. Subtract the 1, we get 4x equals negative 1/2. Divide by 4. It's negative 1/8. This last one's a little bit trickier because 32 is not a power of 4. It is a power of 2, though. 32 is 2 to the 5th. Powers go 2, 4, 8, 16, 32. So it's the 5th power. And then since that's a 4 on the left, we need to change that to also be a 2. So 4 is 2 squared. So this is 2 squared to the x, which is 2 to the 2x. So now the 2's are the same base. Since they're the same base, they cancel out. 2x equals 5. So x equals 5 over 2. Just change both sides of the equation to be the same base, and then set the exponents equal. So remember the idea with domain is you're looking for what you're not allowed to do. So we're trying to find what we cannot raise 3 to a power of. So some of the typical things that you would check is you would check big numbers like 10, 100, whatever. You can do those. 3 to the 100th power is a really big number. You can do it. You can also check negatives. 3 to the negative anything is just going to be another number. It's going to be a very, very small number, like 1/3 or 1/9. It'll be small fractions, but you can do it. You can also do 3 to the 0 power. That's okay. You get 1. You can also do 3 to the fractional power, like 1/2 or 1/3 or whatever. All of that works. So exponential functions, the domain is always going to be negative infinity to positive infinity, just like polynomial functions. Domain's negative infinity to positive. Now to take it to the next step, we're looking at it in the denominator. We know denominators aren't allowed to be 0. So the only thing that would ruin this equation is if 3 to the x were equal to 0. That would not be allowed because you can't divide by 0. Is there any power that we can put on 3 that would make it equal 0? 3 to a big number is a big number. 3 to a negative is a fraction. 3 to the 1/2 is like 1.7. You never get 0. There's nothing you can do that will get it to be 0. So that's still negative infinity to positive infinity. -2 doesn't change anything because all it's going to do is give you slightly different numbers as your exponent. If you plug in 2, you're going to get 3 to the 0, which is perfectly fine. There's nothing that would make that denominator equal 0. So it's negative infinity to positive infinity again. Now this last one in blue is different, and you will see one like this in your homework. Again, remember the denominator is not allowed to equal 0. So that means 3 to the x minus 1 is not allowed to equal 0. So take that, we're going to try to solve it. You get 3 to the x cannot equal 1 when you add 1 to the other side. And what value of x would make that be 3? Or make that equal 1? 3 to the 0 equals 1, so x is not allowed to be 0. So our domain is everything except x cannot be 0, so we show that by negative infinity to 0, union 0 to infinity. You just got to take the 0 out of the interval. You should recognize y equals 2 to the x from the parent functions that we've talked about. Y equals 2 to the x. Hopefully you recall that it passes through 0, 0, 1. Because when you plug in 0, you get 1. 2 to the 0 is 1. Plug in 1, you get 2, because 2 to the first is 2. Plug in 2, 2 squared is 4. Plug in 3, that's 2 to the third is 8. Look at all those dots. And then you should remember that it goes through those dots, flattens out, and goes with the x-axis. So there's our graph of 2 to the x. So the domain is left to right. How far does this graph go? So when you look left to right, we got an arrow on the left, so that's negative infinity, keeps going, never skips anything, keeps going up and to the right, so goes forever to the right also. So the domain's negative infinity to positive infinity. We talked about that on the last page as well. Now remember, range is lowest to highest. So there's nothing down here. It starts right here when we're at 0, and then goes up forever. So that's 0 to infinity. We just have to check if we need a bracket or a parenthesis at 0. Do we ever get 0 as an answer? No. Since it never actually touches that, that's an asymptote, which is our next blank. Since it never touches 0, never equals 0, we do a parenthesis. And we have an asymptote right there, which the purple line is showing. That's at y equals 0. Horizontal asymptote at y equals 0. So since there's an asymptote for on the x-axis, it's never going to touch the x-axis, so there is no x-intercept. And then we can see our y-intercept right there at 0, 1. So now when we graph 2 to the negative x, it's the same parent function, 2 to the x, but the negative in front reflects it over the y-axis. Negative in front of the x reflects over the y-axis. So all of our dots, instead of going through those same points as before, they're going to reflect over the y-axis, and they're going to be on the left side. So we still have 2 to the 0 is still 1, but now everything's going to the left. So 2 to the first is 2, 2 squared is 4, and 2 to the third is 8. The same graph reflected over the y-axis. So our domain still is negative infinity to positive infinity. Range, the lowest it goes is still 0, so it's 0 to infinity. Because we still have the asymptote at y equals 0, which means there's no x-intercept, and the y-intercept didn't move. It's still there at 0, 1. Very similar to the last graph. All right, so this is the same parent function, 2 to the x, but now that plus 2 is going to shift it 2 units to the left. So those normal dots were at 1, 2, 4, and 8. But everything is shifted 2 units to the left. So instead of being there, it shifts 2 units to the left. 2 units to the left, 2 to the left, 2 to the left. So you can erase the parent function dots, just keep the shifted. And then draw the graph. Domain, still negative infinity to positive infinity. It doesn't change. Range didn't shift up or down at all, so it's still 0 to infinity. The asymptote didn't shift up or down, so it stays at y equals 0, which means there's no x-intercept. And the y-intercept, that did shift because now it's 4. 0, comma 4. So to solve this equation, all you would do is you type this into your graph, so you graph it. Just plug it in for y1. You don't need to worry about the 0, but you do need to make sure you include all the parentheses. And then since we're looking to see where it equals 0, that means we're finding the roots. We're going to find the roots. On a Casio, that's by selecting G-solve root. And you should see a couple of them. Make sure you have a standard viewing window. Make sure you have a standard view. You should see there's 2 answers. Go on your calculator, G-solve root, and you get 2 answers. You get x equals negative 1.5 and x equals positive 1.5.